Hello and welcome to this first video about the preparation of Aryl Iodides. In this video we'll have a deeper look at the preparation of Aryl Iodides by electrophilic iodination of unsubstituted or metallated arenes, and in a second video we'll review nucleophilic iodinations. As usual, there's a PDF version of the slides under the Posts tab of my channel. Compared to the other aryl halides, iodides have the longest and weakest carbon-halogen bond and are therefore the most reactive and unstable. Bromides, however, are less expensive and almost as reactive as iodides, and often preferred as synthetic intermediates. Common reagents for electrophilic iodination include elemental iodine for nucleophilic arenes, often combined with oxidants or acids to enhance its reactivity. Iodide mixed with oxidants yields elemental iodine or iodine-3 intermediates in situ. N-iodosaccharin is slightly more reactive and less expensive than elemental iodine, and a popular choice. Further options include bis-pyridine iodonium salts or diiodoethylene for metallated arenes. 1,2-diiodoalkanes are unstable and tend to fragment into olefins and iodine. With elemental iodine, one expensive iodine atom is lost as leaving group, and for large-scale preparations, a combination of iodine or iodide with an inexpensive oxidant is therefore preferred. Iodine also tends to sublime out of the reaction mixture, what can cause further losses and mechanical problems. It dissolves only slowly, and because solutions of iodine are black, it is difficult to see when dissolution is complete. A few biologically active aryl iodides are known, for instance the thyroid hormones, X-ray contrast agents like iopentol, the antiarrhythmic drug amiodarone, and the amebicide iodoquinol. But aryl iodides are mostly used as synthetic intermediates. Because of the weak carbon-iodine bond, aryl iodides readily react with metals and are excellent starting materials for various transition metal catalyzed transformations. The Sonogashira coupling with terminal alkynes works particularly well with aryl iodides. Iodoarenes have also been used as catalyst for oxidations, where the iodoarene is oxidized at iodine to yield a more selective oxidant. Because of the weak carbon-iodine bond, the iodination of arenes is reversible, and aryl iodides readily decompose thermally or when treated with strong acids or bases. Iodoanisole, for instance, disproportionates into anisole and diiodoanisole when standing at room temperature in sulfuric acid. Also phenyl iodide reacts this way but requires a higher temperature. Iodophenols are particularly reactive. Here, a triiodophenol was reduced to a monoiodide by heating with a tertiary amine for 6 hours. Aryl iodides do not undergo aromatic nucleophilic substitutions by an addition-elimination mechanism, but via arenes or with the aid of some transition metal. In this example, iodobenzene was hydrolyzed with potassium hydroxide and catalytic copper oxide at 180 degrees Celsius. Without catalyst, a much higher temperature is required, and arenes are formed as intermediates. Hydrolysis of 4 halotoluenes with an excess of sodium hydroxide, for example, gave an almost equimolar mixture of 2 cresols, and the iodide reacted faster than the other halides. Even traces of copper sulfate increased the regioselectivity of the substitution, and the aryl iodide still reacted fastest. Ammonia and ammonium chloride are often used during the workup of reactions, but that's a bad idea if you're dealing with electrophilic iodinations. Iodine and ammonia readily form nitrogen triiodide, a treacherous explosive. Many fingers and eyes have fallen prey to this compound and to the related nitrogen trichloride and tribromide. It is even advisable to keep iodine and ammonia far away from each other in your storage cabinet because both compounds tend to creep out of their containers. Okay, let's check some specific examples. We'll go from metallated and other electron-rich arenes to less reactive arenes and heteroarenes. At the end there will be some examples of cyclizations yielding iodinated arenes and heteroarenes, and as usual a discussion of side reactions. Lithiated arenes readily react with iodine or with less reactive iodinating reagents. The success of these reactions largely depends on the stability of the lithiated arene. Here, to avoid fragmentation into lithium chloride and an arine, the temperature had to be low. Polyhalobenzenes are acidic though, and the lithiated arene in this case was probably quite stable. In this example, bromoferrocene was lithiated and then iodinated with diiodoethane. Iodination occurred mostly ortho to the bromine atom. Aryl bromides and iodides undergo halide-lithium exchange when treated with butyllithium at low temperature. As a byproduct, the corresponding butyl halide is formed, and if the reaction mixture is allowed to warm, butyl arenes result. Addition of an excess of iodine at low temperature, however, gave the expected aryl iodide in this case. The imine remained unchanged. In this example, an aryl carbamate was lithiated with an excess of butyllithium and then iodinated with iodine at low temperature. Only one isomer was formed in excellent yield, but the workup should not have been done with ammonium chloride, as discussed above. The reaction had to be optimized to avoid a benzoxazole byproduct, formed from an intermediate arine. Imines of benzaldehydes or aryl ketones can yield 5-membered palladium chelates. In this example, such a chelate reacted with iodosuccinimide and yielded, after hydrolysis of the imine, an ortho-iodinated benzaldehyde. Thus, with an aniline and catalytic palladium acetate, the regioselectivity of electrophilic iodination of benzaldehydes can be changed from meta to ortho. Aryl acetamides can also form such palladium chelates. Because iodine does not deactivate arenes strongly, twofold iodinations can be difficult to prevent, as in this instance. Here, the intermediate rhodium chelate of an azo compound was iodinated with a mixture of iodobutane and diacetoxyiodobenzene. Benzamides with additional coordination sites can also form nucleophilic chelates. Here, a cobalt benzamide chelate was iodinated with elemental iodine and with silver carbonate as an additional oxidant. Aryl boronic esters are slightly nucleophilic at carbon and can be converted into aryl iodides with iodide and copper catalysts, sometimes without additional oxidant, as in this example. Here, a similar transformation was brought about with an excess of iodine and 5% of copper iodide. Also, aryl silanes are weak carbon nucleophiles and can be converted into aryl iodides with electrophilic iodinating reagents. Here, iodine chloride was used, and the CC double bond of the cinnamate was also halogenated. Phenols are readily iodinated at positions 2 and 4, but selective iodinations are difficult. This example, with 80% of one main product, was quite a success. The iodinating reagent was an alkaline mixture of iodide and hypochlorite, and the reaction was conducted at 0 degrees Celsius for 2 hours. Treating phenols with diacetoxyiodobenzene can yield iodinated diaryl ethers. This remarkable reaction probably proceeded by transient formation of a diaryl iodonium salt, followed by a migration of the phenyl group to oxygen. Resorcinol can be iodinated once between the two hydroxy groups by careful treatment with just one equivalent of iodine. I could not find any example of direct electrophilic iodination of unsubstituted Pyr-Zn. What isn't surprising, because Pyr-Zn is electron deficient and becomes still more electron deficient when mixed with acids. Hydroxypyridines, on the other hand, are quite reactive. In this example, treatment of 3-hydroxypyridine with one equivalent of iodine gave mainly 2-iodo-3-hydroxypyridine. Here, hydroxynicotinic acid was first esterified with methanol and then iodinated with iodosuccinimide, without isolation of the ester. Anilines are similarly nucleophilic as phenols and can be iodinated directly, without protection of the amino group. An excess of iodinating reagent will usually yield polyiodinated products. Here, a monoiodination succeeded with iodine in an aqueous bicarbonate solution. The amino group was probably iodinated first, but compounds with nitrogen-iodine bonds are still strong electrophilic iodinating reagents, and N-iodoanilines will usually isomerize to 2 or 4 iodoanilines. Less expensive than iodine is a mixture of potassium iodide and hydrogen peroxide. In this example, acetic acid was the solvent, and again mostly 4-iodoaniline was obtained. mixtures of iodine with additional oxidants can be more powerful iodinating reagents than iodine alone. Here, a mixture of iodine with diacetoxy-iodobenzene brought about iodination and cyclization of a metacryl anilide. Also, aminopyridines can be iodinated directly at carbon, without protecting the amino group. Here, instead of iodine, a mixture of potassium iodide and potassium periodate was used. The aqueous solution of potassium iodide was added slowly over 2 hours to keep the concentration of iodine low and prevent its sublimation. Benzoic acids with electron-donating groups in positions 2 or 4 can decarboxylate when treated with electrophiles. In this example, strong heating of an anthranilic acid with iodine and oxygen yielded a 2-iodoaniline. Unfortunately, a flammable solvent was used, and such a procedure cannot be scaled up because of the risk of explosion. Oxygen can, however, be replaced by a base, as in these examples. With potassium phosphate and an excess of iodine, 4-methoxybenzoic acid cleanly decarboxylated already at 100 degrees Celsius. 3-methoxybenzoic acid remained unchanged, however, under these conditions. Mixtures of oxygen with nitrogen or carbon dioxide are safer than pure oxygen. Here, a complete iodination of anisole was achieved with an oxygen-carbon dioxide mixture, only half an equivalent of iodine and 10% of iron nitrate. In this example, despite the excess of oxidant, the arene was only iodinated once and with high regioselectivity. Also here, an excess of electrophile was used, and mostly one diiodoarene resulted. 4-methoxybenzaldehyde was iodinated once at the expected position with a mixture of iodine and diacetoxy-iodobenzene. No oxidation of the formyl group occurred. Benzene is less reactive than aryl ethers or alkyl benzenes. With mixtures of iodine and nitric acid, both iodine atoms can be made use of for iodination, as in this example. In this exotic example, iodine migrated from 2-iodonitrobenzene to propylbenzene. A complex mixture of palladium trifluoroacetate and various ligands was required, and I do not see any practical use right away. But this again shows that iodoarenes are sensitive compounds that readily decompose in unexpected ways. Alkyl groups and halides are both ortho and para-directing, and in this instance the site of iodination wasn't easy to predict correctly. Nevertheless, mainly one isomer was formed. Diaryl iodonium salts can be prepared by iodination with iodine and an additional oxidant, metachloroperbenzoic acid in this case, and a strong acid. These products are valuable electrophilic arylating reagents. With mixtures of strong acids and iodosuccinimide, even electron-deficient, unreactive arenes can be iodinated. No oxidation of the formyl group occurred here, but this was a potential side reaction. Strong heating to 170 degrees Celsius of phthalic anhydride with 2 equivalents of iodine and sulfuric acid led to exhaustive iodination. The required additional oxidant must have been the sulfuric acid. Let's check some heteroarene iodinations. Indole is electron-rich and usually reacts with electrophiles at nitrogen and at positions 3 and 2. In this example, however, the benzene ring was iodinated. A combination of copper iodide and terz-butyl nitrite with oxygen can bring about the iodonitration of indoles. The reaction probably proceeded via an intermediate nitrosoindole. Imidazole readily reacts with iodine under alkaline conditions. The product precipitates when the reaction mixture is neutralized and can be filtered off and recrystallized from ethanol. Here, a substituted imidazole was iodinated with a mixture of iodine, sodium periodate, and sulfuric acid and methanol. Pyrazole can be iodinated once and with high regioselectivity. A mixture of iodine and ceric ammonium nitrate in acetonitrile was used in this case. With a larger excess of iodinating reagent and in refluxing acetonitrile, this pyrazole was still only iodinated once at position 4. Another isomer was obtained by lithiation with butyllithium and treatment with iodine at low temperature. Here, an iodinated pyrazole was prepared by addition of acetylhydrazine to an alkynyl ketone, followed by dehydration and iodination with iodine chloride. Two pyridones are tautomers of two hydroxypyridines, and both show similar reactivity. Electrophilic iodination will occur at positions 3 or 5. Here a mixture of cerulic nitrate, potassium persulfate and sodium iodide was used for this purpose. This example shows that position 5 in pyridones can be iodinated selectively in the presence of a benzyl amino group. Quinolines are much more reactive than pyridines because, like a naphthalene, only one of the two rings is truly aromatic. The starting quinoline of this example reacted with iodine and an excess of terz-butyl hydroperoxide in refluxing acetonitrile to a 3-iodoquinoline. Here an aminopyrimidine reacted faster with iodosuccinimide than the 4-methoxybenzylamine substructure or the malonate. Such selectivities, however, are difficult to predict correctly and must be determined by an experiment. Reagents like iodosuccinimide can also bring about dehydrogenations, for instance by initial hydride abstraction, as in this example. Carbocations sometimes rearrange, and here the final unexpected product was a rearranged iodinated pyridone. A huge excess of iodosuccinimide was used, however. I'll show you now some examples of cycloadditions or cyclizations that gave iodinated arenes. Here, Diels-Alder reaction of a silylated alkyne yielded a cyclohexadiene, which was dehydrogenated and iodinated with a mixture of zinc iodide and terz-butyl hydroperoxide. The Diels-Alder reaction required catalysis because both diene and dienophile were electron-rich and would not react with each other spontaneously. Iodinated furanes can be prepared by electrophilic iodination of propargyl ketones with iodosuccinimide. Similarly, hydrazones of propiolic aldehydes reacted with iodine to yield iodinated pyrazoles. As mentioned, most pyridines cannot be iodinated directly at position 3. However, if a propargylamine is condensed with a 1,3-diketone and the resulting enamine then treated with iodine or another electrophilic iodinating reagent, 3 iodopyridines can be obtained. Unfortunately, such strategies often yield products with too many unwanted substituents, but still, this is a simple, quick access to potentially valuable pyridines. This example is similar to the previous one, the only difference being that just one equivalent of iodinating reagent was used. Dehydrogenation did not occur, therefore, and a dihydropyridine was the main product. Iodinated pyridine N oxides have been prepared by addition of nitrite to acrylates. With iodine under slightly alkaline conditions, cyclization and iodination occurred. One possible mechanism would be a Neff-type oxidation of an intermediate nitroalkane, followed by cyclization, hydrolysis and elimination. Another approach to 3-iodopyridines is iodination of certain acetylenic acids. In this example, a mixture of a pyridine and a pyrrole was obtained. This mixture was formed because the acido group added to the alkyne with low regioselectivity. What about potential side reactions? All electrophilic halogenating reagents are oxidants and can cause dehydrogenations and oxidative dimerizations. Treating thymol with iodine and sodium hydroxide, for instance, gave a diaryl ether as the main product. Some metallated arenes are unstable, even at low temperature, what can lead to unexpected products. Lithiation of dibromopyridine, for example, caused the partial migration of one bromine atom to position 4. Here are some more examples, which I'll try to squeeze into the description of this video. There is also a PDF copy of the slides under the Posts tab of my channel. The next video of this playlist is about nucleophilic iodinations, including the iodination of diazonium salts. See you there.